Beautiful thing, isn't it? I'd like to say we got to work on it, but alas, it is only used as a reference image in this video. I'm Raphael. In this video, we'll go over some important piano scale elements that are particularly important for a technician preparing to restring an instrument. We'll cover things like how to capture the data from an existing strings so that a new set of wound strings can be made, why the technician should evaluate the scale rather than just have the set duplicated, and what specifications a string winder will need to build your new custom set. The actual methods and tools of installing the new strings is another topic and another video. Ready? Well, let's get learning some neat stuff about piano scales. So, how do we get the data the string winder needs? Well, one way is to use a large, rather unwieldy piece of butcher paper or brown paper to cover the strings from the hitch pin to the tuning pin and do a rubbing. Let's hope the paper doesn't slip, move, or tear. And I don't think this gives the most accurate data, as the paper has a tendency to bend to fit contours, and it doesn't give accurate diameter information. Thank you, Hans. Another method is just to send in the old strings. Now, this will certainly give the winder the measurements needed, but it would not account for any of the repairs or replacement strings that may not be like the original. And if the original strings were not sent back to you, what would you use to do the quality assurance checks before the new set is installed? Now, some winders have a pretty complete set of scale sticks, a library of original manufacturer's string specifications, but may not have the information for the piano you are working on. The main shortfall of duplication or replication is whatever compromises the manufacturers may have made, or the nuances particular to the instrument you have before you by way of manufacturing process or error will still remain. Properly and accurately capturing the scale data affords the opportunity to address and make better any of these issues, as well as several other potential evaluation of a scale takes some time and some software, or by hiring a technician to evaluate the scale and make recommendations as a service. Okay, that was a shameless plug, and I hope it works. But back to the question, why the time and expense? Manufacturers must control costs. Sometimes that might mean using the same set of strings for a similar but not exactly equal product or model. It's a pretty common thing in the plain wire sections of the piano scale to use the same wire gauge for as many notes as possible to help control manufacturing costs. As technicians, though, it costs us really nothing to change the wire gauge whenever we feel the need. And how about the scenario where the old scale had something other than copper for the string wraps? Soft iron was used in the early 1900s to about 1917, and the weight difference is considerable and needs to be taken into account to have the new strings wound in today's copper alloys. Or what about the case where the instrument was designed for some pitch other than 440? It would be good to rescale the instrument for a 440, but keep the tensions close to the tensions the instrument was designed for. Scale evaluation and modification for the new strings, wound and plain, allows for smoothing the tension, volume, and inharmonicity curves, especially across the plate struts. We'll be demonstrating the evaluation and mathematical relationships of what we can change to the calculated values of the tension, volume, and inharmonicity. We are looking at the original blue and final yellow tension graphs for a 1905 Steinauer upright. Hans will point out the jumps from the last single string to the first two-string unison, and from the end of the wrapped strings to the plain wire. Moving over to the final graph, we'll look at those same transitions. They are smaller and smoother. Volume is a theoretical value that assumes a standard blow with a standard hammer. The assumptions are used to level the playing field, so to speak, to allow visualization of the effects of changing a string parameter, such as mass, tension, or number of strings in unison. Its inverse can be thought of as a resistance to sound production. The data is useful to evaluate the scale. Now here we see not a lot of difference. This is not a bad thing, and may be why this piano sounded and sold as well as it did. The important takeaway is that the final curve is a bit smoother. The changes that helped tension and inharmonicity, as we'll see next, keep the volume curve in good shape. You can see the improvements in the inharmonicity. Most of the changes are subtle, with a reduction of the inharmonicity in the double wounds to match the single wounds a little better, and some smoothing across the plate struts. Inharmonicity is a factor of material stiffness. It's a complicated effect that the piano tuners hear while they're listening to the coincident partials. Basically, the string does not bend right at the termination point, and the stiffness of the wire effectively moves the termination points inward along the string, resulting in a shorter than physically measured speaking length. Now, at the bass frequency, F sub 1, it matters little to none. The dead zones at each of the terminations are accounted for in setting the tension for the desired pitch. But where the dead zones do come into play is in the multiples of the bass frequency. The size of the dead zone does not change for each string segment of the harmonics. A true harmonic is a full multiple of the bass. Let's take a look at the diagram of a string. For a true second harmonic, F sub 2, the vibrating segment of the string would need to be exactly 1/2 the speaking length. But because of the dead zone, the length is shorter than exactly half, making the pitch of the second partial sharp to the theoretical true harmonic. The word partial here is an important distinction because of that radication. This phenomena progresses through all of the partials. The ratio of the dead zone to the effective speaking length of the partial increases exponentially. The constant portion of the formula is referred to as the inharmonicity factor and is expressed in cents, 1/100th of the difference between notes, and is the value in the graphs. By the way, if you had not noticed, both volume and inharmonicity graphs are displayed in logarithmic scales. In a logarithmic display, the distance from 0 to 1 is the same as the distance from 1 to 10 and the same distance from 10 to 100. If the data were displayed in a linear graph, the nuances would be lost. Wow, we are finally at the point of looking at the relationships of what parameters we can change as a piano technician restringing an instrument to the effect on tension, volume, and inharmonicity characteristics. As we go through these examples, keep in mind that the changes and the results don't relate to any actual scale. It's just to show the relational changes, the proportionality and direction of the effects caused by a singular parametric change. All other parameters are held the same. Only the one parameter for each example is altered and the results displayed. Okay, here we go. The first example addresses a change in winding material. Today, copper is the norm, and the values will be the baseline. The main factor is the mass. Soft iron and aluminum are considerably less dense. Silver nickel is a little heavier. As mass goes down, so does tension and volume. Inharmonicity, though, goes up because while there is less mass in the winding, the core has not changed. The stiffness will have increased in ratio to the loss of mass, resulting in a higher inharmonicity factor. The bottom line is that the change in material is significant to scale parametrics. Moving to a change in speaking length, we will use 1/8 inch or approximately 3 millimeters change in both directions. This change could be because of a misplaced bridge pin. But in summary, the length change equates to mass change. More mass means more tension to hold pitch. More mass translates to more energy transferred through the bridge to the soundboard. Both tension and volume are directly proportional to length change. Inharmonicity is inversely proportional because the length here affects the length of the bare core wire. More length then reduces the relative stiffness. It also demonstrates, though, that the better the accuracy in data capture is very important. What happens if you increase the core wire diameter? Well, tension and volume and inharmonicity are all directly proportional. Pretty much like the last example, more mass equals more tension and volume. But why does inharmonicity increase? A thicker core means less flexibility or more stiffness. In this next example, changing the overall diameter of the wrap. The wrap is there to add mass to begin with. So the changes in tension and volume are directly proportional. An interesting thing, though, is that inharmonicity changes very little, if at all. It does change some inversely, but since the mass is added laterally, wound, think of 90 degrees to the core wire, it doesn't add stiffness. Pretty cool, huh? Keeping these relationships in mind will help the selection of the next universal bass strings when needed. We have two other areas of change that can be addressed really at the same time. Step. Step is the distance from the end of the over wrap to the end of the under wrap. The other is the distance of bare core wire from the end of the wrap to the speaking termination. It's really just another step. A change in step, though, results in very little to non-measurable changes in tension and volume, as the overall change in the mass is pretty insignificant. But the length of the step dramatically affects inharmonicity. The longer the step, the greater the inharmonicity. Now that we've discussed the whys and wherefores of scale dynamics, it's time to turn to the data collection and sharing. What specifications does the string winder need? Well, a good start is the hitch pin diameter. The more accurate this is, the less slippage as the string tightens and comes up to tension, and should result in a stable tuning in fewer passes. The distance from the hitch pin to the start of the wrap, and either the length of the wrap or the length from the hitch pin to the end of wrap. Of course, core wire and overall wrap diameters are needed. I recommend allowing the winder to select the under wrap and over wrap wire gauges from his stock, as for the most part we are concerned with the total mass as expressed by overall wrap diameter. These measurements are pretty easy to get or calculate from the old strings if you've decided to simply duplicate the old set. What measurements does a scale evaluator need though? That might depend on the software tool the evaluator is going to use. Since the producer of this video uses ScaleMaster, we'll use the set needed for that software for this discussion. Although the software doesn't care about the hitch pin diameter for any of the calculations, it tracks it and includes it in the printouts. From the raw data standpoint, the evaluator needs hitch pin to the speaking length termination bridge pin. As you see, that's the bridge pin closest to the tuning pin. Using the wrong bridge pin will be disastrous. This measurement is needed for each wound string, as the hitch pins are usually staggered, especially in the bichord and trichord wound string unisons. The distance between the speaking length termination bridge pin, where we last left off, to the start of the wrap. Usually this distance is consistent in the bichord and trichord groups, and an average will work well. This distance is called bridge. The counterpart of that measurement is V-bar, the distance from the tuning pinned end of the wrap to the speaking length termination nearest the tuning pin. That termination may be called V-bar, capodiastro, or maybe an agraph. We also need speaking length of the string, which is from the speaking termination bridge pin to the other termination. Here again, for unisons, they are ideally alike, so use the average. The diameter of the core wire and the diameter of the wound portion are both needed, and also the step length. This is usually the same at both ends. And don't forget the number of strings in the unison. Another important data point is the note number. A0 is note 1, C8 is note 88. This guy has some tools to make the data capture easy and more accurate. To finish this up, let's talk tools. A micrometer to measure diameters. Bring the tension down to make those diameter measurements and then bring the string back up to tension. Or you could also get these numbers while you're taking the strings off the piano. For the most part, the diameters should be in mils. A mil is 0.001 or 1/1000th of an inch. The values can be converted to or from millimeters. You need a good tool to measure the distances. Most any tape measure long enough to cover the longest string will do. It should be capable of 1/16 inch resolution. I picked this one up at one of the conventions. It has the loop to hold onto the hitch pin and is in millimeters with 1 millimeter resolution. Well, that pretty much covers the topic for this tutorial. I hope you enjoyed it and maybe learned something. Write to opportunist.pianoservice@frontier.com if you have any questions, or need a Scale Evaluator service. My thanks to Hans for pointing the way to us. Now, get out of here and do better rebuilds.